Hear me out. Let's just say that in 7 days I will attend an event, and on that event there will be a door. A door locked by a keypad that opens with a key card. Now let's just say, for the sake of the argument, that I will have a temporary access to that keypad to open the keypad to open a door. Now, continuing this line of logic, let's just say as a theory that I would like permanent access, not temporary access. In that case, how could I go about getting permanent access based on a temporary access whilst I have to return the card later on? Well, what I would probably need to do is I would probably need to take the card, I would need to hack it, I would need to duplicate it, I would need to give back the original and keep the duplicate for myself. On a completely unrelated note, today we'll be hacking RFID cards and duplicating them.
Okay, let's start simple enough. What even is RFID? Well, luckily RFID stands for exactly what it sounds like: radio frequency identification. So, if you have some kind of device and if you'd like to prove to that device that you are you for the sake of opening a door, turning on a computer or making a payment, you do it using RFID. This does mean tags like these, or cars like these, or cars like these. But don't you dare mistake these cards with these cards! They're completely different cards and you couldn't mistake.
But actually, how do RFID cards even work? Well, that is a phenomenal question.
Inside of a card, we'd most likely find an antenna and a circuit. This antenna is obviously there to receive data, and the circuit is obviously there to process it. But one thing you might have noticed that's suspiciously absent is a power supply. So where does this power come from? Well, normally when you have some kind of electromagnetism spectrum devices, there are two kinds. The first one uses frequency for data. Think radio, satellite dishes, modules like these, that sort of thing. But there is another kind, the kind where it's used for power, like for example, a microwave, which uses... Oh, hold on, let me just check. Ah, right. Microwaves to heat things up, like a mango. Now, out of these two, which one does our tag belong to? Well, let's pop it open and see. It's actually both. This massive coil of copper is there to power the underlying circuit, so we power it by the action of reading. Simple. And so that's our card, simply elegant and elegantly simple. This means that in order to hypothetically duplicate the card, all we need to do is just read it and write it to the next one, with no problems or foreshadowings or anything of the sorts. Anyway, let's read the card. So, how will we read the card? Well, we'll do it using this Raspberry Pi 5 and this RC522. Whoops, sorry, I meant this RC522. RC522 is the integrated circuit, but we're using the dev board because A, it has an antenna, and B, I have less than 6 days for this project. I'm not designing a custom PCB in that time. So, looking very briefly at the datasheet of RC522, we can see that we can connect to it using I2C, okay, that's pretty standard, SPI, alright, that's probably what we'll use, and UART?
Okay, my surprise at UART being one of the options is kind of difficult to explain and difficult to understand if you haven't dealt with this sort of thing before. But basically, it's kind of like buying a bag of apples and finding an orange inside. Okay, you have two kinds of data movement. You have the one with a clock line, like SPI or I2C, and you have the kind without, which is usually specialized. The ones with a clock line can function for any general kind of data. They're extremely flexible, which is why they function for displays, for segmented stuff, for audio, for, scanners for cards. They can function for anything. When it comes to kind without a clock line, it's usually specialized. So for example, WS12D812s, those are LEDs, and they function without the clock line because of how specialized they are. They basically just display some light, right? They display color, that's it. UART, however, is unique in that it's the only really well-known kind of mode of transporting information that's generalized, really fast, and without the clock line. It's wacky. It's really so difficult to explain if you haven't dealt with I2C and SPI before, because if you have, you will grow to truly appreciate just how wacky UART is. But I won't get into it too much now because 2 videos from now on we will be working on a cooling system and a peripheral system for Fixit, and over there we'll just connect the Raspberry Pi 5 to the Pico via UART, and then I'll explain it more in depth and then we'll have fun. For now, all you need to know is that effectively you can just connect the board using SPI, I2C or UART. Except we can't use UART because even though the module will allow it, the board will not. We truly live in a society.
Now we'll use SPI, which only has one pin. For the power, we also need the ground. And the data, of course, but that's the MOSI data. We also need the MISO data and the clock to drive them, obviously chip select, maybe the reset line for the convenience. Okay, it's simple, right? I promise. Basically, power, ground, self-explanatory. MISO and MOSI just mean master in, slave out, or master out, slave in. So either from our device to the RC, or from the RC to our device. Then the next one is the clock line. So basically the way I always choose to explain it is, if we have our device send a number like this, then this is what it would look like. For each 1 we send a high, for each 0 we send a low. Then we have our reading device, which reads it like so. But that's only in the astronomically unlikely scenario where they are randomly synced up. But if our device reads this at half the speed of our sending device, then what happens? Well, here we can have a bit of a different visualization, with this being the bits we send and these lines representing when we read them. And as you can see, if we read them at the same speed as we send, everything is fine. But if we read more slowly, our red numbers become different than the ones we send. Same thing if we read it faster. So a clock line functions to synchronize the two, to make it clear to both devices when to read, when to write. It effectively just oscillates up and down, low to high, and every single time our clock line switches from low to high, or from high to low, it depends on the implementation, that means our device should read the value sent. Here is the exact same data, but this time represented with a graph. This is the voltage of our data line, and this is the voltage of a clock line. And that's how they change over time. As you can see, whenever our clock oscillates, we just read the data. Then next, the chip select. That's because we can actually plug in multiple devices to our SPI connection, and chip select would be responsible for selecting which one we're writing to. This will be more important in the next video, where I'll be working on this circuit right here. After that, reset, which I'm like 85% certain is the NRSTPD pin. Okay, maybe like 84%. And so that's how it should be connected. Now, after a quick stream where I've connected them, let's talk about the code. Okay, so the explanation for the code is simple, because I didn't write it. I just took this library from GitHub. No need to reinvent the wheel, we are on a tight schedule. Okay, now reading and writing wise, I started simple. Literally, like the library has a simple version of itself inside of itself. So all I had to do is just run this code and it worked. If I hold up the scanner, there we go, it reads the value. Except it worked on this card, that is the standard RFID card with no BS. But what if we wanted to add some BS? It should be running now, and if we take this card, which if I'm not mistaken is an encrypted card, and if I hold up the scanner, as you can see we get an error. Which makes sense, that's correct. We get an error because it's an encrypted card, and we cannot read an encrypted card because encryption, that's how it works, that's how it operates. I don't make the rules. Very basically, let's just say that you have 4 different numbers. Something like 0, 3, 6 and 0. Now these numbers are a secret between you and your friend, Kevin. And you're just freely sharing them around as a goof. But what's that? Well, that is Jared. And Jared is a prick. Both you and Kevin know that Jared is a prick. And if Jared will see your numbers, then you're done for. So you need to hide these numbers in plain sight somehow. Well, in that case, all we need to do is just create a function that takes in 5 inputs, our 4 numbers, and 1 more input that's the key, and then compute the results of that function. Now this computed result will be our encrypted data. Then, crucially, we'd have another function that's a reverse of our function. So if we give it the hash and the key, it will spit back the 4 numbers. Then, once that function is complete, you and Kevin both take the key and you send the encrypted data. Now, if Jared reads the things you're sending, then congrats, it's a jumbled mess. The same exact principle applies to our cards. Yes, the same principle applies to our cards. Our card, instead of storing data, stores encrypted data and the key to access it. And what you need to do is have that key in order to read it. This is MIFARE Classic, and that's this card right here, not this one. That's why it's so important to never mistake them. Whoops, I got them backwards. And so right here is where we enter the domain of the not so simple MFRC5 to do. That's because in order to read these encrypted cards, we first need to crack the encryption. Or we can just use the default key that all cards come with. That is certainly much easier. So let's have a look at what we're doing here. First, we do a bit of a boilerplate to make sure everything is in order. Then we do something called anti-collision. So basically we scan for cards. There could be more than one, so that's why we perform this operation, to get the UID of the card we want to scan. Now UID means unique ID. Once again, makes sense. If we have a whole bunch of cards, they all have their own identifiers to differentiate which one we're talking about. Now, continuing with our code, we select the tag we'd like to talk to, using the UID, and there, we've got contact. Now, what this code does next is a bit... Well, okay, I'll leave that for the next chapter exactly, but basically we first authenticate with our key to make sure that we have access to the data, and there we go. Now we can read up to 3 blocks at a time or write up to 3 blocks at a time. But why 3? Well, okay, whenever you're dealing with computer science, you've always got to look out for the powers of 2. The reason why is kind of obvious, and I've already mentioned it in the past. So it's especially curious that in this case, you can only read 3 blocks at a time. What's up with that? Well, what's up with that is MIFARE Classic 1K. So basically, the simplest-ish kind of MIFARE card. This kind of card has a relatively more complex kind of memory structure, which basically looks like this. The entire card has 1024 bytes. Wow, it's like the name, 1K. And these bytes are divided into 16 sectors, which are themselves divided into 4 blocks. Each block is 16 bytes each, simple as it could be. Now these sectors is what we actually authenticate with on our card, because despite each sector having 4 blocks, only 3 of them are for data, whilst the last one holds the key. Or actually 2 keys and some access bits. The access bits specify what kind of access you have with the keys, and the keys themselves give you the access specified by the bits. But the point is, in most scenarios, key A just gives you access to the data, and it's 6 bytes long. Just a comparison, SHA-256 has 256 bits, so 32 bytes, so 6 byte key is actually relatively short.
This will be the trend of the video, where MIFARE Classic is basically kind of like an obsolete technology at this point, and it really sucks at security. You don't have to trust me, you can just go to Wikipedia, check all the sources and see that almost all of them are just different people hacking MIFARE cards. And listen, I am not a hacker, I'm an inventor. Inventor of things like taxi, a tag with meow meow written on it. Or taxi, extremely light graphical engine made in C in order to debug Fixit. I really gotta stop spending time with CATC, all this community in general. This is just permanently damaging my brain. But it doesn't matter, the point I'm trying to make is that I am not here to break any new ground or pretend I'm a hacker. I am not. I am here with a problem. That problem being a door I have access to temporarily but would like to have access permanently. And I'm just trying to solve that problem. I just wanted to make that clear because I didn't want to stand here and pretend as if I am better at this than I actually am. I am not good at this. All I do is just solve problems, and this time I have 7 days to do so. Hypothetically, of course, this is all just a hypothesis,
Okay, but before we finish up, let's look at what we've achieved so far. We started with the core of Fixit, that being Raspberry Pi 5, which we'll use for processing. Now using SPI, so the voltage, ground, MISO, MOSI, clock, chip select and reset lines, we connect the RC522. Then what happens is our Raspberry constantly sends commands to the module to scan for cards, so that if some cards come close, we'll get back their UIDs. Now once we have their UIDs, we can select one of these cards and it will be the only one that we'll consider from now on. Then if that card is MIFARE Classic, especially 1K, but it would also work for 4K, then we have access to their memory. And from there, for each segment, we can just authenticate with the key if we know the key. That's simple. If we don't, then we'd need to use this program right here to crack the keys. And oh, yeah, I guess I I didn't mention it. This program I've also gotten from GitHub. It can crack the keys on the card if it knows at least one key for at least one sector. We only got there at the end of the project, like 1 day before I had to hypothetically go. That's because I have actually left out quite a lot of things in this video. All the encryption papers, the ordeal module I fried, the card I've accidentally blocked. There were many things that happened throughout all the streams that I've been working on this, but I won't mention it here, because considering how actually simple this project was, this video is already way too long. If you'd like to know more about all of these happenings, just go to my second channel, enjoy the streams when I ping them, I would recommend. But with that in mind, I am recording this after all of that, all of the things have been done, which means that right now would be actually a pretty good time for summary, considering how I don't really have much time. So, what are we gonna do? Well, there are a couple of scenarios. Scenario number 1, no encryption. This would be the perfect case where the safety is equivalent to a tag or the first card we scanned, which means no encryption and the key is just there out in the open. That is extremely unlikely, but hey, never underestimate human laziness. Much more likely, the card will be MIFARE Classic, which means that it will actually follow the typical sector structure and will actually have potential be encryption. However, in scenario 2, I will hope that MIFARE Classic will be encrypted with the default key. If it's encrypted with the default key, that means we can just, well, use the default key. It will basically mean that the people who set it up didn't change the key, and I'm kind of counting on it. But once again, scenario 2, not very likely. Scenario 3, the card is actually encrypted. What do we do then? Well, I did mention the Crypto-C program before, the one I had to tweak in order to actually get it to work. That program can actually crack the keys of a MIFARE card as long as it knows the key of at least one segment. This would be extremely helpful if we had the key to at least one segment, but our entire problem is that the card is encrypted and we're trying to get those keys. So we're screwed, right? Well, not quite. Because Sector 0 is special. Sector 0 does have 2 blocks for data, but it also has 1 block, the first one, for metadata, unlike all the other blocks. So in that case, in scenario 3, I'll just be hoping that whoever set up the system didn't change the key on Sector 0. Why? Well, maybe because they didn't feel like putting the actual access key there and they just left it hanging, whatever. I don't care. We're just hoping that the Sector 0 has the default key. And then we have scenario 3b, which means that it doesn't have the completely default key, which is just all ones, but it does have a standardized key, which also sometimes happens. Different cards, basically from different providers, do come with different keys in Sector 0, and I have gotten myself a list of all of them, and what my script will effectively do is first check for scenario 1, then scenario 2, then scenario 3, and in the case of scenario 3, it will first try to authenticate with the first sector by using all of those keys, and it will just try succeeding. If it succeeds, then we're moving on to the next step, and then we can use the crypto program to crack the entire card in like around 8 minutes tops. Brilliant! Anyway, I do have to go. I have to go and, set everything up. I'm definitely not going to the hypothetical event, because that would be problematic. I'm just gonna go, to no place in particular. Don't mind me. Okay, let's say just hypothetically that Sector 0 was properly encrypted. What would we do then? On paper it was a success, in reality it was a failure. Did you like that? I really hope you did, because it took a lot of effort. It didn't take quite as much time, but I genuinely did research all of the things about RFID cards in less than a week, whilst at the same time building the goddamn machine, coding, fixing the code. It took a lot of effort, in a week. And one thing you might have noticed is that the hexagon does actually have some additional parts I didn't mention, like this whole second layer, or this circuit right here, or this circuit right here. And that's because this isn't just an RFID cracker. That project is called Fix It, and it's something I've begun working on around 2 weeks ago. It's
kind of different. It's difficult to explain what it actually does, but the point is, this video is the start of a series in which I'll expand Fix It and add more things to it, and I feel confident saying so because video number 2 and video number 3 projects are already well underway and I'm almost finished with both of them. But I'm not gonna lie, prototyping and doing all of those things, that's really expensive, and I don't really earn much money on YouTube. I earn less than a Polish minimum wage, which is not a lot. So if you'd like to support me, if you'd like to actually give me money to prototype and to make things proper, then my Patreon. Yup. Give me money. There are some standard perks, like for example, sometimes I do Patreon-only previews where I preview videos that I don't upload. Sometimes there are special things, like for example with Remco, when I'm planning a quantum field TV live stream or quantum mechanics live stream, then we really often do tests about these live streams for patrons only, etc, etc, all the etceteras. If you subscribe, I would really appreciate it. If you'd like to see me work on these projects in real time, then I recommend my second channel where I do live streams of me working on these projects in real time. But that's enough sending out, because all good things eventually have to come to an end, just like this video. And so remember kids, don't do anything illegal, especially if you get caught. And for now, that will be it. Thank you everyone so much for watching and have a great day. Bye!